Hi, everyone. Today I'm going to go over Lesson 8 in Unit 2, which is on periodic table trends. This is actually the assignment that accompanies the first part of the lesson that we went over earlier this week. So if we look at our first slide here, let's take a look. What you're going to see is a listing of all of the metals, nonmetals, and metalloids. So the metals are in this blue color. The metalloids, which have properties of both metals and nonmetals, they're in the green color. And finally, the nonmetals are shaded in yellow. You can see that most of the periodic table is in fact made of metals. Now, what we're going to do in our activity now is we are going to take a look at some properties of metals, metalloids, and nonmetals. So let's take a look. If you look at this screen, you can see that we have properties of all three things. So first, we know that metals are solid. So that means that at room temperature, they exist as a solid. There's actually one exception to this, and that is mercury. So I wrote on the screen that mercury is a liquid. It's the one thing that doesn't follow that pattern. Okay, the second thing is that they are ductile. That means you can stretch the material. So metals can be stretched into thin wires. The next one is that they have a metallic luster. That's a fancy way of saying, sorry about that. That's a fancy way of saying that they are shiny. So metals are shiny. The next word there is malleable. Malleable means that you can bend and shape them. So for this word, I'm going to write bendable. And the last part is they are good conductors, and that means of two things, heat and electricity. So these are just two examples of metals, silver and iron, things that you are probably familiar with. The second one is called metalloids. They have properties of both metals and nonmetals. So properties of metals and nonmetals. They are also shiny, but metalloids tend to be brittle. That means they break apart easily. And they are considered semiconductors. So they're not great at conducting electricity, but they do conduct it at a very low level. And then finally, in our last column, we have nonmetals. So nonmetals shaded in yellow all the way on the right side of the table. They can be solids, liquids, or gases. They tend to be dull. They are brittle, and they are insulators, which means they are non-conductors. If you want to think about what the term insulator means, think about any wire that you use, like the wire that you use to plug in your cell phone or your computer. That has a rubber insulation on it. So in the middle of that, there are these copper wires that connect your computer to the outlet, but you don't want to get electrocuted. So they coat those wires with this rubber coating, which is made of an insulating material. The other place where you might hear about insulation is in your house. So the walls of your house and the attic of your house probably has insulation in it. And that's to keep the heat in the house in the winter, where we're headed, or in the summer to keep the heat out of the house. So insulating prevents heat from entering or exiting. Or in the case of a wire, electrical conductivity from entering or exiting. Okay, let's take a look at our next slide. So this says identify each element as a metal, a metalloid, or a nonmetal. So you can go back up and look at your colored periodic table, the one that's colored blue, yellow, and green, and you'll find out that fluorine is a nonmetal. Germanium, which is the second one, is an example of a metalloid. Zinc. Zinc is something that you should be familiar with. That's a metal. Phosphorus is another nonmetal. And finally, lithium is our last example, and that's another metal. Okay. The next one is a new periodic table, and this one is colored based on the different names that are given to each group. So group 1, if you notice this orange color here, that's everything in this first column except for hydrogen. This is known as the alkali metals. The next one is group 2, so I'm going to circle that here. So group 2, this right here is known as the alkaline earth metals. It's this right here. And then the other two groups that I'm asking you to know are the halogens. So this right here, that's this group. This is group 17. And finally, all the way on the right side of the periodic table, we have group 18, which are the noble gases. So I am only asking you to know those 4 columns. Those are the ones that we're going to refer to most often. Let's take a look at the next slide. So give 2 examples of elements from each category. So I'm just going to pick the first 2. So for the noble gases, we'll pick helium and neon. So 2 examples. From group 17, we can pick fluorine and chlorine. From group 1, remember, it does not include hydrogen, so the next 2 are lithium and sodium. And then finally, from the alkaline earth metals, the first 2 are beryllium and magnesium. So 2 from each of those 4 columns on the periodic table. Okay, looking at the next part. Now we have some questions that we're going to answer. So the first one says, what trend in atomic radius do you see as you go down a group or family on the periodic table? And then what causes this trend? So the first part, and we talked about this in our last class, is that as you go down a group, we start to see the atomic radius get bigger. So atomic radius increases in size. And the major reason for atomic radius getting bigger is there is an increase in the number of energy levels. Second, what trend in atomic radius do you see as you go across a period? So we're going to look at a simulation in our next class that's actually going to go over this. But as you go across a period, you actually start to see atomic radius decrease. It gets smaller. So atomic radius decreases in size. Left to right. The reason why atomic radius gets smaller, as you go across a period, the number of protons in the nucleus goes up. That means the nucleus gets stronger. So the stronger the nucleus is, the better it is at attracting electrons, and it actually causes the atomic radius to decrease. So more protons in the nucleus makes the nucleus stronger, and it's better able to attract those electrons, pull them in tighter. All right, so in this exercise, what we're supposed to be doing is identifying which one is the bigger of the pair. So let's look at, we're going to highlight these. So let's look at our first combination. We have aluminum and boron. Now, what might help is if you draw an arrow on your periodic table to show where atomic radius gets bigger. So if I draw an arrow here, atomic radius gets, so it gets smaller this way, so it gets bigger going to the left. And then here, it gets bigger going down. So the bigger side here versus here, or here versus here. So let's look at our first pair. So we have aluminum and we have boron. So aluminum is right here and boron is right above it. So look at our arrow. Whichever one is lower is bigger. So in this case, since aluminum is lower, aluminum is going to be the larger of the two. So we're going to highlight aluminum. Letter B, we're comparing sulfur and oxygen. So here's sulfur, here's oxygen. Because sulfur is lower down, sulfur is going to be the larger one. The next part, we have bromine and we have chlorine. So on the periodic table, bromine and chlorine are over here. Bromine is the one that is lower down. So bromine is going to be the larger one. Oops. The next one we have is a combination of sodium and aluminum. So if we look at, here's sodium, here's aluminum. Look at our arrow. Our arrow points in this direction. That means sodium is the bigger one. So we're going to highlight sodium over here. The next ones that we're going to look at are oxygen and fluorine. Oxygen and fluorine are over here. Oxygen is further to the left side, so oxygen is the larger one. And then finally, magnesium and calcium. So magnesium and calcium are right here. Whichever one is lower down is the larger one, so calcium is the larger one in this case. Okay, we will have a similar question to this on our test or quiz. Let's take a look at our next slide here. The next part we're going to move into is talking about ionization energy. So ionization energy is the energy required to remove an electron, basically to pull an electron off of an atom. Oops. The next question. Is it easier to form a positive ion, which means that we're removing an electron, from an atom that has a high ionization energy or an atom that has a low ionization energy? So high ionization energy means that it's going to cost a lot of energy to try and rip that electron off. So that's going to make it harder. Low ionization energy means you don't need a whole lot of energy to remove it. So that one would be easier. So to answer the question, it is easier to remove an electron from an atom or from an element with a low ionization energy. Okay, number 9 says, use the concept of ionization energy to explain why sodium forms a +1 ion, but magnesium forms a +2. Now, this goes back to something that we learned in our atom builder when we were putting together protons, neutrons, and electrons, because this is based on the number of valence electrons, electrons that are in the outermost energy level. So sodium has 1 electron in its outermost level. So it will form a +1 ion when the electron is lost or removed. On the other hand, magnesium, which is in group 2, has 2 electrons in the outermost level. So it will form a +2 ion when the electrons are lost. In this case, 2 electrons would be removed. So sodium, 1 electron in its outermost level. When it loses that electron, it forms a positive ion because now you have more protons than you have electrons. When magnesium forms an ion, it's going to lose 2 electrons because it has 2 in the outermost level. So it forms a +2 ion. Okay, moving on. If we take a look at question number 10, it says, what trend in ionization energy do you see as you go down a group? The trend that you see for ionization energy is the opposite of what you saw for atomic radius. So going down a group, ionization energy decreases. Ionization energy decreases as you go down a group. And that's because as the atom gets bigger and bigger and bigger, the electrons in the outermost level, they're very far away. So here's the nucleus, here's those outer electrons, they're very far away. So it's easy for an atom to come by and steal that electron. So we're going to put here Y, as atom increases in size, outermost electrons can be removed more easily. So outermost electrons can be removed more easily as the atom gets bigger. Same thing with question number 11. What trend in ionization energy do you see across a row or period? So again, it's opposite. So ionization energy increases across a period left to right. Now, why is that? On the left side, you have less protons. On the right side, you have more protons. The more protons, the better attraction, the harder it is to remove an electron. So, elements on the right side have more protons. And therefore, it's harder to remove an electron. Okay. So we're going to do the same thing that we did here and highlight whichever one is larger, but this time our arrows are going to point up and they're going to point toward the right side. So let's look at our first combination, lithium and beryllium. So here's lithium, here's beryllium. Whichever one is closer to the right is going to have a greater ionization energy. So whichever one is further to the right. So in this case, our answer is going to be beryllium. For letter B, we have sodium and potassium. So for letter B, we have sodium, which is right here, potassium, which is right here. Sodium is higher up. So that means it's smaller, more difficult to remove an electron. So we're going to go with sodium for the answer here. Our next combination, chlorine, which is right here, and silicon, which is right here. Chlorine is further to the right side, so it's going to be a higher ionization energy. So we're going to circle chlorine or highlight chlorine. The next one that we're going to look at is calcium and barium. So here's calcium, I underlined it in green, and here's barium. Calcium is higher up, so calcium is going to be harder to remove an electron from. We're going to highlight calcium. The next one that we're going to look at is phosphorus and argon. So here's phosphorus, I'm circling it in blue here, and here's argon. Argon is further toward the right side, so it will have the higher ionization energy. And then in our last combination, we have lithium and potassium. So here's lithium, here's potassium. Lithium is higher up, so this one is higher up, so it will have a greater ionization energy. Okay, on to our last part here. So this talks about electron affinity. how strongly an atom is attracting electrons, bringing electrons in toward itself. So electron affinity, a measure of an atom's attraction for electrons. Okay, next, what trend in electron affinity do you see as you go down a group? This trend matches the trend for ionization energy. So lower electron affinity at the bottom, higher electron affinity at the top. So as you go down a group, electron affinity decreases. As you go down a group, electron affinity decreases. Now, why is that? At the bottom of a group, the atoms are bigger. That means the nucleus is further away from any electrons that it's trying to attract. So the nucleus is so far away that it's not going to do a very good job of attracting electrons. So the larger it is, the weaker the attraction. We're going to say larger atoms have a weaker attraction for electrons. Now, as you go across a period, just like ionization energy, it's going to get stronger. So as you go across a period, left to right, the attraction for electrons increases. Now, what causes this trend? So why does that happen? And we're going to say atoms on the right side of the table have more protons and are better at attracting electrons. So atoms on the right side of the periodic table have more protons and are better at attracting electrons. So stronger nucleus can attract electrons more. Okay, let's look at our final activity here. So for the last time, we're going to pick whichever one has a greater electron affinity. And again, this trend, just like ionization energy, goes up and over. So looking at our first combination, we have calcium, which is right here, and we have gallium, which is over here. Since gallium is further to the right, we're going to say that gallium has the stronger electron affinity, the higher electron affinity. Okay, the next combination that we're going to look at is lithium. Lithium, which is right here, and oxygen, which is over here. Because oxygen is further to the right, we're going to say that oxygen has the greater electron affinity. The next combination is chlorine, which is right here, and sulfur. They're right next to each other, but chlorine is further to the right. So we're going to say chlorine has the greater electron affinity, whichever one is further to the right side. Letter D. We have bromine and astatine, or arsenic rather. So bromine, which is right here, and arsenic, which is right here. Bromine is further to the right. So bromine will have the higher electron affinity. The next one is barium. Barium is right here. Strontium is right here. Strontium is higher up than barium. So strontium will have the higher electron affinity. And then our last combination. So our last combination is oxygen and sulfur. So here's oxygen and sulfur. Oxygen is higher up, closer to the top.